In class exercise 6, chapter 4, problem 4.144. The distribution of the distribution of soil loading on the bottom of a building slab is shown in the figure. Replace this loading by an equivalent resultant force and specify its location measured from point O. So what we need to do is we need to replace all this like distributions by a single point load. This is what we are looking for, Fr, and we would like to measure distance of that force from O. So this is point O. This is what we need to do. So two-step approach. First, we reduce the distribution to point loads and then from point load to equivalent resultant load. Our coordinate system assumption is that going up is positive for this like problem. Now there are four distributions. If you closely observe this height of the rectangle here is only 50 foot-pound, while this height here is 100 foot-pound. So it's not one line. Okay, so there are two different distributions. So the four distributions that we can see here is this triangle distribution, that's number one. Sorry, rectangular distribution, that's number one. Then this triangle distribution, that's number two. Then this triangle distribution, that's number three. And this upper rectangle distribution is number four. So let's reduce this distributions to point load. So for number one, its equivalent point load is the area of the rectangle, which is 50 multiplied by 12. Okay, so that's here. $50 times 12, and this is in pound. For the second triangular distribution, it's 1/2 times base times height. So the base is 12, and the height here is this height. Now, since this is 50 and this point is 300, it's 300 minus 50 is this height. Once again, this is 50 and the total is 300, so 300 minus 50, so this is 250. So it's 1/2 times 250 times 12. That's the second distribution. Okay. Third is again triangle, so it's this time the height is this, which is 300 minus 100, so it's 200 pound. So it's 200, 1/2 times 200 times 9. And the last one is rectangular distribution, which is 100 times 9. Now their locations relative to point O, that is this point O here. For the first one, it's a rectangular distribution, so half of the distance, so that is 6 foot. For the second one, it's triangular distribution, so its centroid is located at a 2 by 3 of 12, which is 8 foot. For the third distribution, which is triangle, its distance measured from this reference line is 1 by 3rd of 9, which is 3, but plus 12, because 12 is up to this point, and then 1 by 3rd from this line, because the base is here. So total is 15. And for the final rectangular distribution, it's half of this, which is 4.5 plus 12. So that is 16.5. Okay, so that's equivalent force system. Now we can reduce this forces to single resultant measured at distance d from O. So let's write down the equation for equivalent resultant load. So sum of Fr is sum of resultant force. Going up is positive, or acting up is positive. So this is literally summation of all these numbers. So 50 times 12 plus 1/2 times 250 times 12 plus 1/2 times 200 times 9 plus 100 times 9. You add them together, we get 3,900 pound. Now that's a big number, so we will write this as kilopound. So 39 KIP, where KIP stands for kilopound. That is equivalent resultant load. So this one here is 3.9 kilopound, where P is small. And now to find the exact location of this force, we calculate the moment of all these forces about O will be same as the moment of this one force about O. So moment of resultant force about O counterclockwise is positive is equal to sum of moments of all the forces about O. So the sigma MO is coming from this diagram, and this is coming from here. So that's FR times D, that's counterclockwise, so it's positive, equals sum of moments of all these forces. So it's 50 times 12, that's only the force, but its distance is 6 foot. So multiply by 6, and all the moments are counterclockwise, so positive. Plus this number is force multiplied by distance. This number force multiplied by this distance, and this force multiplied by this distance. So plus 1/2 times 200 times 9 12, 200 times 12 times 8 is the distance, plus 1/2 times 200 times 9 times 15 is the distance, plus 100 times 9 times 16.5 is the distance. Now we know the value of Fr, so we can actually substitute Fr is equal to 3900 times D, and then this equation just copy it here. So from that you calculate D, and that's 11.3 feet. That's the final answer. So this D is equal to 11.3 feet. So what this means that we can reduce. So all these machines, they apply the load on the soil, and that distributed load can be replaced by a single point load of 3900 pound acting at 11.3 feet measured from O. That's the solution. Now in class exercise problem 6.2. So until now, all the distributions that we have considered are either the standard rectangular shape or a triangular shape. But this time we are going to consider a distribution which is given by the parametric equation W as a function of X. So for this distribution, W is function of X, and that function is given here. So how can we reduce this distribution to a single point load Fr and measure its distance from point A? So that's what we need to do now. So replace the distributed loading, replace the distributed loading with an equivalent resultant force and specify its location on the beam measured from point A. So A is a support, which is like pin support, and we need to measure the distance from A. Now, if you carefully look at this equation, we will get these numbers as we substitute the value of x. For example, in this case, when you write x equal to 0, then this is 0, this is 0, and it's 100. So x is measured from A, because that's the origin. So at A, value of load is 100. When you substitute x equal to 15, you will get load at B, which is here, and that's 370 pound per foot. And in between, at any location, the load is given by this equation. So that is the distribution, and for that we will make use of these two equations, which are we have seen them during the presentation. This is the equation for equivalent point load. So equivalent point load for this problem going down is positive can be calculated using the area under the, so it's 0 to L, area under this like distribution, which is 0 to L Wx dx. So we can just write down 0 to L, it's x squared plus 3x plus 100 times dx. Now integrate this with respect to x. So this will be x cubed by 3 plus 3x squared by 2 plus 100x, and then substitute x equal to 15 minus x equal to 0. So x equal to 0 is 0, but when we substitute x equal to 15, we get 2962.5 pound or 2.96 kilopound. And that is the resultant force. So we already get this answer, which is 2.96 kilopound KIP. And now to find the exact location of that from A, let's call this X bar. So to find X bar, we will make use of this second equation, which is the X multiplied by Wx dx integral divided by Wx dx. So this integral Wx dx is nothing but our load. We just have done that here. So that's 2962.5. Now what we need to do is we need to multiply this with one more X because it's the moment now. So it's load multiplied by distance is moment, and then we integrate it over the length. So X bar is equal to integral 0 to L x multiplied by Wx dx divided by integral 0 to L Wx dx. So I'm substituting for the denominator. I'm just writing 2962.5 because we just have calculated this in the previous step. Now this is integration 0 to L x multiplied by x square plus 3x plus 100 times dx. So now x is multiplied with each one of these terms. So this will become 0 to L x cubed plus 3x square plus 100x dx divided by 2962.5. Okay, and we'll continue that, and now integration of that is x cubed divided by, sorry, x to the power 4 divided by 4 plus 3x cubed divided by 3 plus 100x square divided by 2, and then substitute 0, like 15 minus 0 for x. So substitute x equal to 15 here. So it's 15 to the power 4 by 4 plus 15 cube plus 50 multiplied by 15 square. And then whole thing divided by this number gives us 9.21 feet. Because you see, remember this is distance measured from A, which is 9.21 foot. Okay, so final answer is this distance is 9.21 feet. And that's the end of this solution. So let's look at it one more time. So how we have made use of these two equations. We have calculated the resultant load by integrating the function over the length, and then we calculated x bar, the exact location, by dividing the moment of distribution with the total